Hi guys, welcome to today's video lecture. Today I want to go over a couple of misconceptions that are always prevalent when dealing with Newton's three laws of motion. Because ultimately where we're going to go with this is with tension force problems, which can be kind of tricky. To add a layer of difficulty to them, I'm going to speak in Wookiee. So if you don't know how to speak in Wookiee, you might want to turn on the caption. All right, that's enough of that. Well, anyway, April Fools, ha ha ha. Let's get down to business. Actually, okay. So there are some misconceptions that do occur when you're dealing with Newton's three laws. So the first of which is the difference between mass and force, and or mass and weight, I should say. One really clever or one really visual way to represent the difference is by thinking of an astronaut on the surface of the planet and one in space. The astronaut on the surface will have a mass and a weight. Their mass is maybe 95 kilograms, while their weight is 210 pounds approximately. But in space, that weight goes away. They are weightless, but they're still made up of the same stuff, so they still have that same mass. So what exactly is weight if it's something that can go away? Well, weight is a very specific type of force. It's the force that's exerted on an object due to gravity. Remember, if you see anything in blue, make sure you write it down so you fully understand it. Weight, which in this case is a force, is equal to your mass times your acceleration. So since 99.9999% of your experience occurs on or near Earth's surface, where the acceleration due to gravity is constant, which, if you remember, is 9.8 meters per second, you can pretty much ignore that acceleration and directly compare weight to mass, which is what a lot of people do. Despite them not being the same thing, they can be identical properties when the acceleration is constant. But as soon as you leave the surface of Earth, that acceleration is no longer the same, so it doesn't make sense to compare them anymore. Well then, what is mass? What you're used to thinking of mass is, or the earlier definitions of mass that you get in elementary school maybe, is that mass is how much stuff something is made out of, or maybe how much matter it's made out of. But a better way to describe it, or a more sophisticated way, is in terms of inertia. Inertia describes an object's resistance to changing its motion. So something that's really heavy, something that's really massive, is very difficult to change its motion. Think of these two buckets here. We've got one bucket full of sand and one bucket that's empty. If you push them equally with both of your arms, with both of your hands, one is going to be much easier to push than the other. That's because this one has less inertia. And inertia is measured by an object's mass. So things that have more inertia are more massive, or things that are more massive have more inertia. So that is a good way to be thinking about mass and inertia from this point going forward. This is one of the questions that was on the exit ticket yesterday. Only 51% of you got this right. In addition to measuring how much matter an object is made out of, mass is also a measurement of an object's inertia. So make sure that you guys are solidifying that concept that inertia and mass are pretty much one and the same. All right, so let's get into Newton's three laws of motions and where they may trip you up. So our first law is the law of inertia. Unless acted upon by an outside force or an unbalanced force, an object is going to want to stay at rest if it's already at rest, and an object that's in motion will want to stay in motion. I'm recording this on a smart recording software, so there's a little bit of it's a low frame rate to begin with, and these animations also low frame rate, so I'm not too sure how this is coming out for you guys. But this image does a pretty good job, if not comedically, of illustrating the law of inertia. So you have this person on a resting plate, I forget what they're called, and they are at rest, and they're not secured, so they want to stay where they are in space. And as a truck drives away, they slide off the back because they're at rest and they want to stay at rest. And then if you look at this woman up here, as she's moving with the truck and she falls off, she wants to stay in motion, so she keeps rolling on the floor. Objects with more mass inertia are resistant to change in motion again. All right, here's a good example too. So here we have a person free falling down onto a net, and all these leaves are at rest, so they want to stay at rest, and then they eventually fall down when the force of gravity is acting upon them. I think this is a cool one. All right, our second law. This is nothing more than an equation that you guys are actually probably familiar with. Force equals mass times acceleration. And one way to interpret this formula is to say that to accelerate a mass, you need a force. A force not equal to zero. So to change the motion of something, to change its speed or to change the direction that it's traveling, you need a force. This equation can be rearranged to solve for any of these three variables. So acceleration is equal to force times mass. And in doing so, it kind of changes the interpretation of the formula. So if you look at it from this perspective, where force is equal to mass times acceleration, you could say that the greater the mass and acceleration of an object, the more force it has, because mass and acceleration will be directly related to force. If you rearrange it to solve for mass, you might say that the more massive something is, the more force you need to move it. So it's not going to accelerate very easily. And if you rearrange it to solve for acceleration, you might be able to say that if you increase the force on an object, it'll accelerate faster. So it's just three different versions of the equation. Depending on what two variables you know, you can solve for the third one. All right, so here's where this trick comes into play. This tricky question. Only 30% got this right. These are numbers that I specifically chose because you would get these numbers if you multiplied these things in a certain way or divided them in a certain way. But there is there's an actual clever way to solve this. So there's actually two ways to solve it. So let's take a look at them. The acceleration due to gravity is 9.8 meters per second. We know that. The skydiver, however, is only accelerating at 8.7 meters per second because of the wind resistance that they're feeling. And it's slowing down their acceleration, or decreasing, I should say, not slowing down, I should say decreasing. I'm going to change that. Decreasing the acceleration by 1.1 meters per second every second. That's the difference between 9.8 and 8.7. So that means that this must be the acceleration of the wind, right? This is their acceleration due to gravity. This is their deceleration, I suppose, due to wind. And then this would be, or their negative acceleration. And this is their net acceleration. So if the acceleration due to the wind is 1.1 meters per second every second, and if the mass of the skydiver is 67.2 kilograms, you just simply multiply mass times acceleration, and you would get the net force, or the force of the wind acting on them, which is 73.92 newtons. Another way to solve this is to solve for the force of gravity, which is 9.8 times the mass. So 9.8 times 62.7, that would give you this much. Then solve for the net force, which is 8.7 times the mass, and that would give you this much. And then simply find the difference between them, which is the same answer as that one. All right, so here's another common misconception when it comes to acceleration and gravity problems and force problems. What falls faster, an apple or a watermelon? Well, some of you might be tempted to think that a watermelon is more massive and it's heavier, and so it probably falls faster than an apple. If you give it some thought, though, and you think about F equals ma, the clever ones might think that because the apple has less mass, it's easier to accelerate. Therefore, the apple is going to fall faster because a watermelon is difficult to accelerate. But that wouldn't be true either, because there's one more thing that you have to take into account when you're talking about objects that are falling due to gravity. And that is that mass has a direct impact on the force of gravity. So massive things, like the watermelon, do have more inertia and are more difficult to accelerate, but they're more attracted to Earth by gravity because they have more mass, and mass and gravity are directly related. Smaller things with less inertia, like the apple, are easier to accelerate, but they're less attracted by the force of gravity because they have less mass. So it turns out that these two offsetting principles make it so that every single object near the Earth's surface will accelerate towards the Earth's surface at 9.8 meters per second. So that's a very common misconception, that things don't fall the same. Now there are, I don't want to say exceptions to this rule, because everything does fall at that acceleration, but you can change that acceleration by changing the net force, because you may have a different surface area that will change how much air resistance is pushing you up. So if you are an elephant with a parachute, you might fall faster, or you might fall slower than an apple without a parachute. So depending on how you take advantage of the air resistance by changing the shape and the amount of surface area that's exposed to the atmosphere as you're falling, that can change your acceleration. But you're not really changing the acceleration due to gravity, you're changing the air resistance that you're feeling as you fall. All right, so here's a cool demonstration of this. This is an astronaut, I forget which one it is. up in the 60s or 70s, and he took a hammer and a feather to the moon's surface where there is no atmosphere. And so because there's no atmosphere, there's no air resistance, and the vacuum in the vacuum of space, the hammer and the feather fall at the exact same rate. And this experiment has been replicated on Earth in a giant vacuum chamber. So if you wanted to Google that, I'm sure you could find the YouTube clip pretty easily. Again, I don't know if these videos are translating well to YouTube because of the frame rate of my recorder, but they're kind of interesting nonetheless. So here we have a massive object, which is the car, and here we have someone who's less massive on a motorcycle, and there's an interaction. There's a force interaction of him kicking the car, and because he's so much less massive than the car, he's the one that accelerates more to the right. Now the car does accelerate to the left ever so slightly, because there is a force that it's experiencing, but it's not nearly as much as this guy who's going to accelerate due to his smaller inertia. Same thing here. This is just classic, kid kicking a rock. Ooh, there we go. So this kid has mass and inertia. This is more like a rotational inertia thing. It's not a great comparison for F equals ma because there's some spinning involved of his body around a central axis, but it's still kind of fun to watch, Whoop. All right. All right, so here's an F equals ma problem. It looks like we're solving for a force, so it's pretty direct. I'm not going to walk you through the whole thing. If you want to solve it, pause the video now, and then I'll click on the blue thing as soon as you've done unpaused it. Okay, hopefully you took some time to solve it, and basically you're just going to get this solution. Another one. So again, if you want to try to solve this on your own, pause the video now. Okay, so if you got stuck there and you want a hint, I bolded a very crucial word here. It's falling. So if you know something is falling, what is the rate at which it is falling? Pause now if you think you got the answer, and unpause when you solved it. All right, so here is your answer. Things fall at 9.8 meters per second, so the force divided by that is your mass. Okay, lastly, this problem gives you a mass, and it also provides the force, so you want to solve for the acceleration. Go ahead and pause if you want to solve. And welcome back. Here is the solution. All right, so our last law, and this is the one that gives students the most difficulty in terms of fully understanding. It's often summarized as for every action, there is an opposite and equal reaction, but I really don't like that. It's a very misleading definition, and I'll tell you why. It gives the impression that there's two forces that are involved, an action force and a reaction force, and that one precedes the other, much like a loud noise, which is an action, might cause you to jump, which is the reaction. And it makes it seem as though one force occurs before the other force, and that's simply not true. One reason is because there's only one force. There's only one interaction, right? So when you're looking at this rifle, in this video, there's actually two separate force interactions. The first is the firing of the gun. So the bullet leaves and the rifle goes back. That's one interaction. And then the second, totally separate interaction is the rifle hitting his face, but that's neither here nor there. The crucial thing here is understanding that when you have an interaction between two objects, there's only one force that governs that interaction. So here is a summary of how this might occur. This is a very large elephant hunting rifle or something. Anyway, it doesn't really matter. The bullet fired has the same force as the gun's recoil. It's one force that governs that interaction. What makes a bullet deadly, I suppose, is two things. It has a small mass, so its acceleration is very high, right? Remember, F equals ma. The force is also concentrated on a small point. The force of the rifle, however, is spread out over the rifle's stock, and the rifle is much, much more massive than a bullet or a projectile. So it's not going to accelerate to those deadly speeds or those dangerous speeds, although this guy still kind of looks like he got hurt. So the big thing here to take away is that when objects collide, or when gravity pulls on something, or when magnets are interacting, there's only one force governing that interaction. But because the different objects may have different masses, they will accelerate differently. So this question was pretty misleading. Which of the following is true regarding the force of gravity between the Earth and a person in free fall? So I'm sorry, the question isn't misleading, but many of you did not get this right, only 47% of you. So the second runner-up is that the Earth exerts a greater force on the person, and I was thinking that that is going to be the common misconception, which is why I put that answer in here. The Earth does not exert a greater force on the person. The Earth and the person experience the same force, right? So here's a good way to think of this. You have one interaction, which is the force of gravity. The properties of Earth is that it has mass, and it's going to accelerate due to this force. And the properties of the person is that it too, that person too has a mass, and they will accelerate due to the force. But because the mass of the Earth is huge, its acceleration towards the person will be very, very small. So small that it will be imperceptible. You won't even notice it. However, the person's mass is tiny compared to the Earth, insignificant compared to the Earth. So as a result, its acceleration is going to be absolutely huge. But it's still one force that exists between the Earth and the person. It's just one force, and it's the exact same thing. So the same concept was illustrated in this question, where a student releases a cart from the top of a ramp. It rolls down the ramp and hits a block at the bottom with 100 units of force. The block is knocked over. Which statement best describes what happened? So again, a lot of you chose, a plurality chose that the block is going to apply more force to the cart, but the cart will apply some force to the block. That's the same thing as this, right? I'm surprised that these are, it's pretty much the exact same question, just a different format. But the correct answer is that they will apply exactly the same force on each other because it's just one interaction. That impact between the cart and the block happens once. It's one interaction, it's one force, and the different masses of the different objects will cause their accelerations to be different. All right, so let's just recap one more time. Misconceptions due to Newton's three laws. First, mass is a measurement of inertia. It measures how resistant an object is to change in its motion. More massive things don't want to change what they're doing. If it's at rest, like a massive boulder, it's going to want to stay there. If it's moving like a semi-truck and it hits a small thing, it's going to plow right through it because it has a lot of inertia. Number two, F equals ma. This isn't so much a misconception, but you do need to be able to rearrange those variables to solve for any of the three force, mass, or acceleration. Solve any of the three variables. And then number three, this is the big one. The way that you should approach Newton's third law is that every interaction is influenced by one force that is felt equally by the objects involved. What's different is how they respond to that force through their acceleration, which is influenced by their mass, aka their inertia. So the action and reaction concept can be very misleading, and I don't really like that. Anyway, that's it for today. Thank you for watching until the end, and I hope you guys are staying healthy as we remain socially distant. Remember, the only way to get through this together is to not be together. All right, have a good day.